Welcome to the second part of Randomized Algorithms lecture. If you haven't seen the first part, link is in the description. First problem, catch them all. When you encounter a Pokemon, it's a random out of n types. How many Pokemon will you encounter, on average, before seeing all n types? The statement could also say that you collect some stickers, and every time you collect a random sticker out of n types, and what is the expected value of tickers you get before you collect all n types. We will use a very important fact that if an event that you repeat has probability p to happen, then the expected value of how much time you wait till it happens is 1 over p. If we have probability p, then expected value is 1 over p. We had an example of that in the first part, where we tossed a coin that had probability half to give you tails, and then on average you need to wait 1 over half, which is 2 times, till you indeed get tails. In this Pokemon problem, we will first for sure catch the first Pokemon, then eventually second one, and so on. But what happens at the very end? At the moment when we have already n-1 types, then the probability to catch that one last type, no matter what ID it is, if they are numbered from 1 to n. Anyway, if we have n-1 already caught, then the probability to catch one last one is 1 over n. So the expected value of time you wait till you catch it is n. What about the second last Pokemon? So this was when we already caught n-1. But what if we caught n-2 different Pokemon? Now the probability to catch a new one is n over 2 over n, because there are two types that we are looking for out of n. So the expected value of time till we get one of those two missing ones is n over 2. Then a moment earlier, for third last type, this is the probability to catch it in a single try, in a single encounter. So this is the expected value of time we wait till that happens, and so on, plus n over n. And such a sum is around n log n, actually n natural logarithm of n. This is a very, very important sum, you should know it well, because it's called Harmonic Series, by the way, if you want to look it up. Now, if we don't look at the process backwards, what happens is the time we wait to catch the first Pokemon is just 1. In the first try we will get it. Then second one will be n over n-1, which is slightly bigger than 1, because maybe, just maybe, we will repeat that first type. Let's say among types 1 through 10, first you caught type 6. Then there is some small probability that you will encounter 6 again, so that doesn't help, but almost surely you will caught one of the other 9 types. So this probability is slightly bigger than 1, then bigger, and eventually, if you already have n-1 Pokemon, n-1 different types, then you need to wait a lot of time to catch that last one of them, on average n. Consider the same process, but this time we stop immediately when we encounter the same type of Pokemon again. If you encounter types, let's say 2, 6, 8, 7, and then again 6, you stop. What is the expected value of that time? And we don't need to compute the answer precisely. We are just interested in the estimate. Say, for n equal to 1 million, do we need 100,000 encounters? Do we need 500,000? Likely not, because in that many tries for sure something will be repeated, almost for sure. How many do we need? Turns out that the result is around square root of n. And this is called birthday paradox. The birthday paradox name comes from the fact that if there are 365 days in a year and you have some number of children in the same class, it is enough to have around, I think, 25 children to have very, very high probability that there will be 2 children that have the same birthday day. Even though number 365 is quite big, and you might guess that maybe I need around 100 children to get probability, say, half, to get the same birthday. But the important thing is, if there are k objects, each generated randomly between 1 and n, then there are around k-square pairs, actually k choose 2 pairs, and each of them, not independently, but each of them has probability 1 over n that those two children, say child number 1 and child number 5, that they have birthday on the same day. So it isn't entirely correct, but we can say that roughly k square over n is probability that one of those events happen. Actually, events are not independent, we cannot just sum like that, we could get probability bigger than 1, but to make this to be O of 1, say to make it half, not something very, very small, it is enough to get k equals square root of n. So in this problem, how many encounters we need before getting the same type of Pokemon twice? It is enough to get roughly square root of n encounters. This is called birthday paradox, and sometimes you will use it as something in complexity of your program. In this part of lecture, I assume you know what hashing is. And with hashing, you should also understand what is hash collision, and we'll talk about it here. Let's say we compute hashes modulo p, some prime number. So every hash will be between 0 and p minus 1. There are p possible values. It is very, very important to understand the difference between those two problems and their probability of hash collision. In one problem, we are given a long string and we should answer queries. Is this substring the same as some other substring? We can use hashes for that to answer in constant time. For a long string, if I compute just hash of this substring, hash of that substring, I can compare those two hashes. And the probability of making a mistake, if those two strings are indeed different, is 1 over p. We assume that every hash is a random-ish number from 0 to p minus 1. If two strings are different, they will produce the same hash with this probability. Because first string gives us some hash, then second one will be one of p values and one of them would give us collision. For p equal to, say, billion plus 7, this is a very small probability. Likely you will have around million queries, maybe 100,000 queries in a problem. So this even times 1 million is still small enough. Again, you shouldn't just multiply probabilities like that. If you repeat something million times, the probability that this happens at least once isn't just probability times 10 to 6, but we can estimate that this way. So this even times 100 tests is then 1/10, which isn't very, very small, but likely this value will be smaller. Likely we have 100,000 queries, and then probability of having a collision is 100. If you want to make sure that you're right, you can use bigger modulo, or you can use 2 modulo values. Then probability of hash collision is much smaller, because it's 1 over p times 1 over q, if q is that other modulo value. But this was acceptable at least. There is different type of problem though. Given a bunch of strings, find 2 equal strings, something like that. Or given a bunch of substrings, each described as LR, compute for each of them hash, and find a pair that is the same, so has equal hashes. Because then, when we have k different strings, each of them will give us some hash, let's say that they are all different, then from birthday paradox, we know that already if k is around square root of p, square root of modulo value, then there should be a collision with some not small probability. If you choose modulo as 1 billion and you have 100,000 strings where you should find a pair that is equal, you will likely have a collision, even in one test, not even saying about 50 or 100 tests. So remember, if you just compare two values of hash to check for equality, one modulo is usually enough. But if you have a bunch of hashes and you want to find 2 equal ones, or like count pairs of strings that are equal to each other, then you need 2 modulo values to decrease the probability of hash collision, because of birthday paradox. Change of topic now. How to randomly shuffle an array. In C++ there is function random shuffle, but how would you do it yourself? On the left you see code in C++ for that, on the right in Python. I will talk over C++ code, but if you prefer Python, just look on the same thing on the right. The thing is, what I wrote here, for every index from 0 to n minus 1, choose j to be random index from 0 to n minus 1 as well, and swap two values, this is not correct random shuffle. And so is this one on the right. Correct one is in the bottom. For each index from 0 to n minus 1, choose j to be random number from 0 to I, and then swap. So what is the difference? Let's say that we have numbers 5, 2, 8, 9. The first one takes number 5 and it swaps it with one random integer out of all four. Then it does the same for second number and so on. The second piece of code, the one that is correct, when it has 5, it does nothing, it swaps it with 5 itself. Then when it has 2, it swaps it with one random value in the prefix, maybe with itself, and so on. So two questions. Why is this correct? And why was the first version incorrect? We can prove that this version is correct by induction. If prefix of some size, let's say this size 2, is correctly random shuffled, correctly means that each permutation has the same probability of happening, then when we take that next number 8, what happens is in the prefix of size 3, 8 will be in random position 0, 1 or 2. So each position for 8 is equally likely, and then other positions are randomly shuffled already, because numbers 5 and 2, that shorter prefix, was correctly random shuffled. So if you swap 8 with whatever number on the left, still other numbers are equally likely to be permuted in each of k factorial ways. So this is a correct random shuffle. How to explain why the first one isn't correct? There are two ways. One way is to analyze what happens for array of size 3, 1, 2, 3, or whatever, 5, 10, 15, and to say what will be the probability of each outcome at the end. But the other way, that doesn't have any cases, is to compute how many ways we have for something. Here we run rand modulo n times. So there will be n power n different possibilities, outcomes. For each of them we will get some permutation at the end. And the thing is, even for 3, this value is 9, but the number of different permutations is 6. This is not divisible by each other. If we got, for example, 30 possible outcomes, then maybe 5 of them correspond to one permutation, 5 of them to the other, and so on. But it is impossible that there are 6 different results, and here 9 possibilities of what our code does, and each of 6 possibilities, each of 6 answers is equally likely. If this value was 30 instead, then it would be possible. Maybe each result we would get in 5 different ways. But 9 is not divisible by 6. In general, n power n is usually not divisible by n factorial. Here comes a trick that will sometimes allow you to get rid of one logarithm in complexity. If you want to read more about it, you can go to Radeusz's blog in Codeforces, link is again in the description below the video. There is some hidden sequence, and you can ask queries about this sequence. Queries of form, is this number greater equal something, greater equal 10 or not? The interactor will tell you yes or no. Then you ask, is this one greater equal 7, and so on. Your job is to find the maximum element in this hidden sequence using 103,000 queries. N is up to 100,000. So you cannot just binary search each element separately, because the complexity of that would be O of n times logarithm of values of, I don't know, max of AI, and this is too big. That would be 100,000 times 60, too much. We need to get complexity around O of n. Now you should stop the video and think about this problem for maybe like 10-20 minutes, because it's very cool. That naive solution that separately binary searches every element is unnecessary because we aren't interested in the whole sequence, we just want to know the maximum. Let's say we binary search the first element and it turns out to be 9. Then for second element, after some iterations of binary search, we know that it's smaller than 9, smaller equal than 9, we can stop already. But if we get here 12, then for the next element, we are only interested in its exact value if it's greater or equal than 13. After some time, let's say that we indeed binary search all the values. There is here 4, 5, 6, 13, 2, and so on. And we are, let's say, right here. We know the prefix. The thing with this next value is that it will very rarely be maximum element so far. If the sequence is, let's say, random, then the probability that ith element is biggest so far is 1 over I. Stop! I almost forgot to add something very important in the lecture. The sequence is not necessarily random. Maybe organizers created a sequence that is just increasing, and then every next number will be bigger than maximum so far. So the thing that I forgot to add is we can randomly shuffle the sequence ourselves. But wait, we don't know the sequence. So what we can do is we can gather all the indices from 0 to n-1, random shuffle this vector or list of indices, and ask about indices in this order. And then we can say that for every next index that we ask about, every next element that we ask about, it is random compared to other ones. Its value is not random, but the fact that the ith element that we ask in this random order will be bigger than everything so far, the probability for that is small. Back to the video, if this is ith element. Because in the prefix there is some maximum element, maybe multiple of them. The probability that this is first of those biggest elements is only 1 over I. If there are multiple of them, then this is not the first biggest one. If this is a unique biggest value, the probability of that is only 1 over size of prefix. And we can use the fact that this probability is so small. When I have this new element, my first query will be, is this value greater or equal than maximum so far, plus 1? So greater or equal 14, if maximum so far was 13. If yes, then I binary search this value exactly. If not, then I skip. If I get answer no, which is very likely, I minus 1 over I, then I say, I don't care about this value, let's continue. This is probability that this is that biggest element so far, for which I will indeed run binary search, what means that the total expected number of queries is, for first number we have 1 over 1, that this is biggest so far, times logarithm of 10 to 18 of that, let's say m will be limit from the statement, plus 1 over 2 times logarithm of m, and so on. What we have in total is the sum from I1 to n of 1 over I, the probability that this is biggest so far, times log of m, which is in total, we know already that the sum of those ratios is log of n, natural logarithm of n, times log of m, which is very small. This is around, what, 20 times 60, around 1000, and it's okay. Plus, each element for each element, we will ask this one extra query. Is this greater or equal to 14? Let's sum this up. For every next element, we will ask if it's greater than maximum so far. Likely it isn't. For each element, for sure, we ask one query. This is n queries in total. Plus, for some of them, it will indeed be bigger than anything so far. Then we binary search the exact value. And that takes time log of m, 10 to 18. From those extra queries, we get around this many of them, log of n times log of m, which is around 1000, plus n queries that we ask for sure. For every next element, we ask if it's biggest so far. And in total, we get around n queries plus log square, what shouldn't exceed our 103,000. There are two more problems that I leave to you as an exercise. One of them was pointed out in Codeforce's comments. Thanks for that. It's a very cool problem that I remember from like 5 years ago, but I forgot about it when preparing this lecture. You're given three matrices, A, B, C. Check if the product of A and B is equal to C. You should try to solve this problem only if you know what matrices are, and some linear algebra is useful here, but because this is randomized algorithms lecture, you have a hint that there is something randomized going on. And the goal is to do it without just multiplying two matrices. If you want to then look up the solution, you should Google Freiwald's algorithm. I'm not sure how to say it, but it's written here. The second problem is how to estimate the value of pi without any formulas, without knowing like Taylor series, some sums that converge to pi. How to estimate pi using randomized algorithm. Solution will be in the description of this video as well. That's it. Tell me in the comments what other lectures I should prepare. See you next time. Bye.